Okay, and a minute ago, I lied when I said we weren't going to talk about this for a couple of days. I need to talk about this really quick. So earlier we were looking at a matrix up here, 1, 3, or 1, 2, 3, 6, and we were wondering about the range of that matrix. So let's answer that question. Oops. So my kind of question here is, what's the range of 1, 2, 3, 6? And my clue to you is to think about the column multiplication picture, right? So I'm going to apply this to some vector. How big does this vector have to be in order for me to apply this?
2 by 1.
Good. It's got to be a two-dimensional vector because this is a something by 2 matrix, right? So I'm going to apply this to a vector AB. I know that feels a little weird. I'm just throwing scalars in here. You'll see why in a sec. If you apply this, there are 2 pictures, right? Oops. Sorry. So there are 2 pictures here, right? What are the 2 pictures for matrix multiplication? Picasso and Rembrandt? Stick figure and photorealism? Ultragore. No, what are the 2 pictures for matrix multiplication?
Row and column.
Good, they're row and column. So my claim is that for this one, you want to think about the column picture. So what does the column picture say this multiplication comes out to?
A times 1, 3, B times 2, 6.
Good. A times 1, 3 plus B times 2, 6. Okay, now, don't be overwhelmed. But what is that? If I thought about all the possible A's and B's, right? What is this thing?
2A equals B.
Oh, yeah. So for one thing, you could notice that this vector here is actually a scalar multiple of 1, 3. So we could collapse this a little bit. We could say, all right, so that's A times the vector 1, 3 plus 2B times the vector 1, 3. And that further collapses into the scalar A plus 2B times the vector 1, 3. Okay, good. That's worth noting. We're going to need that in a second. But what is this thing specifically right here? Where I took these 2 vectors and multiplied them by some constants and added them together? What's a word for that? It starts with L. Rhymes with combination.
Linear combination.
Good, that's a linear combination. So the set of all linear combinations, this thing here represents the span of those 2 vectors. Now, the thing that Cody noticed is that those 2 vectors aren't 2 vectors. Those are a vector and a scalar multiple of itself. So that span is actually just the span of the vector 1, 3. You guys see that? So what's the range of this particular matrix? It can only output things of the form a constant multiple times the vector 1, 3. Where did that 1, 3 come from? Where did the 1, 3 come from originally here? Where'd you get that thing?
Well, it comes from the first column of the matrix, but I feel like that's a unique quality of this specific matrix.
Good. That's really good skepticism, Jordan. That's really excellent. So let's think about a matrix A that's made out of some columns. So if A is made out of columns, column 1, column 2, on and on. Let's see. Let's make M columns, I guess. You guys see this? Then the range of A is going to be the span of all the columns, right? You guys see that? Now, hot question. We just went over this a little bit. Remember how a span, right? The set of all the linear combinations of a bunch of vectors? Remember how that's automatically a vector space? Or a subspace? The first problem we did today was like part, I don't know, D or something, and we were all just like, yeah, duh. And then we skipped it. So, because this is a set of linear combinations, it automatically contains all the linear combinations, ergo it's a subspace. This thing is such a special subspace that it gets a name. So the range of A is automatically going to have a name. It's going to end in space, and it's going to have an of A. And then I need you to fill in this blank here. So if the null space is all the things that go to 0, what space is made out of all the columns? Don't get creative.
Column space.
It is the column space, exactly. And the column space is the range. Not the codomain. It lives in the codomain, but it is the range. You guys recognize that distinction now? So if A is M by N, right? This is a map from Rn to Rm, right? And the column space, where does the column space live? Oops, what did I screw up here? You guys see what I screwed up? Shit! I screwed something up very badly. What is it? Oh my god! I'm panicking! Help! I need a mathematician or an adult. How many columns did I put in here? I said it has M columns, right? And then I wrote down it's M by N. So I need to fix one of these. I'm going to say this is, in order to keep my usual notation, I'm going to say there are N columns here. Okay, now my question is, where does the column space live? Does it live in the domain or in the codomain?
Codomain.
Good. This lives in the codomain.
But I only know that because you said that like 30 seconds ago.
Good. That's fine. So this is the codomain is actually equal to Rm, right, as a vector space. And I've been sloppy about putting vector hats on these. I'm assuming you guys know that Rm is a vector space. And then just quick reminder, where did the null space live?
In the vector space or in the space of A, or what, I don't know how you would phrase it, but
So what's the null space? It's the set of things that get
mapped to 0.
Mapped to 0. So it's in the domain.
Oh.
You guys see that? It's a little hard to keep track of here because we've got a lot of moving parts, right? We've got a function and there's a lot of stuff going on. The null space lives in the domain. The column space lives in the codomain. Right? And the column space is the range. So if you want to take something from this, this is the part to take today. Good with that?